Welcome to the Joy of Architecture. Today, we're taking a deep dive into a topic that's absolutely crucial if you're building or working with modern applications: how to secure a microservices architecture. It's definitely a complex landscape, isn't it? Our mission today is to give you really actionable strategies, best practices across every layer of security, so you can walk away feeling truly well-informed.
That's absolutely right. Microservices, they offer incredible agility, scalability, but they fundamentally change the security game. You're not defending one big castle anymore. Think of it more like a sprawling city. Lots of different buildings, roads, entry points.
That's a great analogy, the sprawling city.
Exactly. And we'll unpack why this whole distributed nature brings unique challenges and, more importantly, how to tackle them head on. Our core philosophy for this deep dive, it's going to be a defense in depth strategy combined with a zero trust model. Because in this world, the mantra has to be never trust, always verify.
Okay, never trust, always verify. I like that. Let's unpack this. So, securing this sprawling city, what makes it so fundamentally different from that old castle approach?
Well, it's the very things that make microservices attractive, right? Their autonomy, their independent deployment cycles, those are precisely what complicate security. First off, you've just got a vastly increased attack surface. Think about it. Every service, every API, every little communication point is a potential vulnerability. It's not like one big application with a single front door.
Right, it's like having hundreds of doors and windows instead.
Exactly. And that naturally leads to this huge complexity of distributed security. You're trying to manage policies, keep things consistent across maybe dozens, even hundreds of independent services. It's really easy for practices to become inconsistent, configuration drift sets in.
So, not just more doors, but maybe each door has a slightly different lock, or maybe no lock at all if you're not careful.
Yeah.
How does the communication between these services factor in? Is that a major risk?
Oh, absolutely. That's where inter-service communication risks really bite. Those channels between services are critical vulnerability points, a flaw. A vulnerability in just one service can spread incredibly quickly. You can get these cascading failures across the system.
Okay, that sounds bad.
And then there's data management challenges. Your data isn't all in one place anymore. It's spread across different services, maybe different databases. Making sure that data is consistently protected, preventing leaks or tampering, that gets much trickier.
And keeping track of it all.
Mm.
The logs.
That's the observability and log management headache. Microservices generate just massive amounts of logs from all sorts of different places. Trying to sift through that, correlate events across services to find the root cause of an issue or spot a security incident, it can feel like finding a needle in a haystack without the right approach. You absolutely need centralized observation.
Wow. Okay. This really does sound like it needs a fundamental shift in mindset. You mentioned defense in depth and zero trust earlier. Can you break those down a bit more?
Sure. So defense in depth is all about layers. Think multiple layers of security controls, physical, technical, administrative. The idea is if one layer fails, if an attacker gets past one control, there are other layers behind it ready to catch them. Your solution should be complementary, maybe even overlap a bit, providing redundancy. It's just pragmatic, right? No single control is ever perfect.
Okay. Layers make sense. Like an onion or maybe a medieval fortress with multiple walls. And zero trust. You said never trust, always verify.
Exactly. Zero trust is the core operating philosophy, especially crucial for microservices. You assume nothing is safe by default. No traffic, whether it's coming from outside or moving between your own services internally, is trusted automatically. Only communication that is explicitly allowed, explicitly verified, gets through. This is so vital because that old idea of, oh, it's inside our network, it must be safe, that's a huge vulnerability in a distributed system. Security has to be baked in right from the very beginning.
Built in from the start. That leads us perfectly into foundational security practices. Where do we actually begin putting these ideas into practice?
It really starts with secure by design, or what people often call shifting left. This just means embedding security thinking into every single stage of the software development lifecycle. From the moment you start designing a service, all the way through coding, testing, deployment, finding and fixing a security issue early in design is way cheaper and faster than finding it in production. It also helps build a culture where everyone thinks about security.
So it's not just a security team's problem later on.
Precisely. And hand in hand with that is the principle of least privilege. This is fundamental. You grant users, processes, services only the absolute minimum permissions they need to do their specific job, nothing more. For microservices, this means service A only gets access to the specific data or resource it absolutely needs from service B. It minimizes the potential damage, the blast radius, if one service does get compromised.
Containment, basically. If one part fails, it doesn't bring the whole house down. How does this apply at the network level?
That brings us neatly to network segmentation and microsegmentation. So traditional segmentation is about dividing your network into larger isolated zones, maybe based on environment or function, to control traffic flow. Microsegmentation takes that concept much, much further. You apply really granular policy-based controls down to individual workloads, applications, maybe even specific containers or Kubernetes pods.
Wow, okay, so like tiny little firewalls around almost everything.
Kind of, yeah. It drastically limits an attacker's ability to move laterally within your network if they do breach one part. In the Kubernetes world, Kubernetes network policies are the native way to do this. They let you define very specific rules about which pods can talk to which other pods. You can and should adopt a default deny stance, nothing talks unless you explicitly allow it. That's zero trust in action at the network level.
That sounds powerful, but also incredibly complex to manage manually, defining rules for every single pod interaction. That sounds like a recipe for errors or just giving up.
You've hit the nail on the head. That complexity is a major pitfall. Mapping every dependency, manually tagging everything, keeping it all up to date in a dynamic environment. It highlights something really crucial. Manual security configuration just doesn't scale for microservices. It's unsustainable. This is where automation becomes not just nice to have, but an absolute fundamental requirement. Tools exist, things like Illumio, Akamai, Guardicore Segmentation, Calico. They help visualize traffic and automate the creation and enforcement of these fine-grained policies.
Right. Automation isn't a luxury, it's essential for survival here.
Oh.
Okay, so we've segmented the network. Now, how do we manage who or what gets access within this highly distributed system? Identity and access management, IAM.
Yes, IAM is absolutely critical. In a microservices world, you need robust ways to manage both user identities and, importantly, service identities. A core principle is centralizing user authentication. Use a dedicated identity provider and IDP. This streamlines things hugely. For the actual authentication protocols, you're looking at standards like UpAuth 2.0, which is really an authorization framework, letting applications access resources on behalf of a user without getting their password. And then OpenID Connect, OIDC, builds on top of Oath 2.0 to provide the identity verification part. Think log in with Google, or Okta, Auth0, they use OIDC.
Okay, so OAuth 2.0 and OIDC for users. What about the tokens they use?
That's where JSON Web Tokens, or JWTs, come in. These are compact, self-contained tokens, usually digitally signed. A central authentication service issues a JWT containing claims information about the user, their permissions. The beauty is your back-end microservices can then independently verify the token's signature without having to call back to the authentication service for every single request. It's stateless, which is great for performance and scalability.
And these JWTs, can services use them to identify themselves to each other too?
They can, yes. JWTs can definitely be used for service-to-service authentication as well. But there's another, often stronger pattern for internal communication.
Which is?
Well, first, baseline is encrypting traffic with TLS, just like you do for external HTTPS. That gives you confidentiality and integrity. But for internal service-to-service communication, mutual TLS or MTLS is a significant step up. With MTLS, both the client service and the server service have to authenticate each other using certificates. It's bidirectional authentication.
Ah, so they both prove who they are before talking. That sounds very zero trust.
Exactly. It aligns perfectly. Implementing and managing MTLS across potentially hundreds of services used to be a massive pain, though. This is where service meshes like Istio or Linkerd have become so valuable. They provide a dedicated infrastructure layer, often using sidecar proxies alongside your services. Service meshes can automate the rollout and management of MTLS, handle certificate rotation, provide fine-grained access controls based on service identity, and give you observability into that internal traffic.
Okay, so service meshes make MTLS practical at scale. Once a user or service is authenticated, how do we manage what they're actually allowed to do? Authorization.
Right. Authentication proves who you are. Authorization determines what you can do. The simplest approach is role-based access control, RBAC. You define roles like admin, editor, viewer, and assign permissions to those roles. It's straightforward for simpler cases. But microservices often need more granularity. That's where attribute-based access control, ABAC, comes in. ADAC makes decisions based on attributes of the user, the resource they're trying to access, the action they're taking, even environmental factors like time of day or location. It allows for incredibly fine-grained policies.
Fine-grained sounds good, but also sounds complex to define and manage again.
It can be, which leads us to policy as code, and specifically tools like Open Policy Agent, or OPA. OPA is an open-source, general-purpose policy engine. You define your authorization policies using a declarative language called Rego, completely separate from your application code. This means you can version control your policies, test them, update them dynamically without redeploying your apps. OPA can handle RBAC, ABAC, even more complex models. It's become a CNCF graduated project, which speaks volumes.
So decoupling policy decisions using OPA makes complex authorization manageable and scalable. What are the typical trip-ups with IAM and microservices?
Well, integrating different systems, IDPs, MFA, SSO can be complex. User lifecycle management, provisioning, deprovisioning always needs care. But a big one, especially with MTLS, is the certificate management burden we touched on. In dynamic microservice environments, MTLS certificates often need very short lifespans, maybe days, sometimes even hours. Trying to rotate these manually across hundreds or thousands of services is basically impossible. It will lead to outages. So again, robust automated certificate lifecycle management is absolutely essential for MTLS to be viable.
Automation, automation, automation. I'm sensing a theme. Okay, let's pivot slightly to API security. APIs are the front door for many microservices, right? The API gateway seems key here.
Absolutely. The API gateway acts as that crucial central enforcement point for external client requests. It's like the main security checkpoint for your city. It handles essential security functions, authenticating incoming requests, applying rate limiting and throttling to prevent denial of service or brute force attacks, enforcing access policies. It can also integrate with a web application firewall, WAF, to block common web attacks like SQL injection or cross-site scripting, XSS. Plus, it handles routing, logging, and decouples your clients from the internal service structure.
So it's doing a lot of heavy lifting on the security front. What about securing the APIs themselves beyond the gateway?
Good point. You need secure API design principles from the very beginning. This includes using strong authentication, like OAuth 2.0, ensuring data integrity and confidentiality with HTTPS everywhere, minimizing the data exposed by any API endpoint only, return what's necessary, implement rate limiting, use least privilege for API keys or tokens, and keep your dependencies up to date.
Are there common patterns of API attacks we should be particularly aware of in a microservices context?
Definitely. The OWASP API Security Top 10 is the go-to resource here, and several risks are highly relevant. API 1. Broken object level authorization is a big one. This is where an attacker manipulates an ID in a request, say API orders 123, changes it to API orders 4v6, and suddenly accesses someone else's order because the backend didn't check ownership. API 2. Broken authentication covers flaws like weak tokens or not handling token expiration properly. API 4. Unrestricted resource consumption, failing to implement rate limiting, making you vulnerable to DOS. And API 9. Improper inventory management is interesting, basically, not knowing all the APIs you have exposed, leading to shadow APIs that aren't documented or secured properly.
Shadow APIs sound dangerous. Okay, moving down the stack. Microservices usually run in containers, orchestrated by Kubernetes. How do we tackle security at that layer?
This layer is absolutely critical. Vulnerabilities in your containers or Kubernetes setup can undermine everything else. For container image security, best practices start with using minimal base images. Don't pull in huge OS images with lots of unnecessary tools and libraries. They just increase the attack surface. Use trusted base images from reputable sources. And critically, implement regular vulnerability scanning using tools like Trivy, Claire, Snyk, or Anchor. Scan images before they get deployed, and ideally, monitor them continuously. Also, avoid running containers as root whenever possible. Use non-root users inside the container.
Okay, secure the images. What about Kubernetes itself?
Kubernetes security has several key areas. First, secure access to the Kubernetes API server. Don't expose it directly to the internet. Use TLS for all communication. Implement Kubernetes RBAC role-based access control rigorously. Apply the principle of least privilege to users and service counts. Use namespaces for logical separation and potentially separate RBAC policies. Enforce pod security standards, PSS, using Kubernetes built-in pod security admission controller or more advanced tools like OPA Gatekeeper. These define policies like preventing privileged containers or host network access. And a big one, Kubernetes stores its configuration, including secrets and etc. By default, secrets in, etc. are just base64 encoded, not truly encrypted. You must enable encryption at rest for secrets in the API server configuration.
Right, base64 is just encoding, not encryption. That's a common misunderstanding. It feels like the dynamic nature here really changes the game compared to traditional server security.
It absolutely does. Traditional static security scanning tools often struggle with the ephemeral nature of containers and the complexity of Kubernetes. That's why real-time monitoring, runtime security tools, and automated policy enforcement are so essential. You need visibility into what's actually happening inside your running containers and your cluster. Common pitfalls include overlooked vulnerabilities in base images, accidentally running privileged containers, insecure default configurations, and just the sheer challenge of maintaining consistent security policies across a rapidly changing environment.
Okay, another critical area, secrets management.
Mhm.
Passwords, API keys, certificates. How do you handle these securely in a distributed system without them ending up hard-coded somewhere?
Yeah, secret sprawl is a massive problem. Secrets get hard-coded in source code, checked into Git, put in config files, environment variables. It's a nightmare for security and rotation. The solution is centralized secrets management solutions. Think dedicated, secure secrets vaults. Tools like HashiCorp Vault, AWS Secrets Manager, Azure Key Vault are designed for this.
What makes these vaults better than, say, environment variables?
They offer several key features. Dynamic secret creation is a big one. The Vault can generate database credentials or API keys on demand that are short-lived, maybe only valid for an hour or even minutes. They provide automated secret rotation, fine-grained access controls based on identity, who or what service can access which secret, and detailed activity monitoring and auditing who accessed what, when.
HashiCorp Vault comes up a lot. How does it typically integrate into a microservices environment, like with Kubernetes?
Vault has several excellent integration methods. The Kubernetes auth method allows pods to authenticate with Vault using their Kubernetes service account token. Then you often use the Vault agent sidecar injector. This automatically adds a small Vault agent container to your application pods. This agent handles authenticating to Vault, retrieving secrets, and even keeping them renewed automatically. It can inject secrets as environment variables or files, making it transparent to the application. It elegantly solves that "how does the first secret get there" problem, and strongly encourages the shift from risky static secrets to much safer, dynamic, short-lived credentials.
Dynamic secrets sound much better. And auditing access is key too, right?
Absolutely. Auditing secrets access is non-negotiable for security and compliance. You need that trail to understand who did what, investigate incidents, and satisfy auditors. Vault and similar tools provide robust audit logs.
Okay. Related to secrets, what about other sensitive data that's just sitting in databases or files?
Yeah.
Data at rest encryption.
Also crucial. Data at rest encryption strategies protect data even if the underlying storage is compromised. There are various methods. Standard symmetric key encryption like AES-256 is common. Databases often have built-in features like transparent data encryption, TDE. A powerful approach is application-level encryption, ALE, or field-level encryption. Here, specific sensitive fields are encrypted by the application before they even hit the database. This gives very fine-grained control. But the absolute critical point here is key management. Your encryption is only as strong as how well you protect the keys. Using a secure key management system, KMS, rotating keys, not storing keys alongside the data, these practices are paramount. Losing the keys means losing the data.
Right. Encryption without key management is like locking a door and leaving the key under the mat. Okay, let's zoom out a bit and talk about the whole process. Security in the SDLC or DevSecOps, we touched on shifting left. Can you expand on that?
Sure. Shifting left is really about integrating security throughout the entire software development lifecycle. It's a cultural and process shift. Instead of security being a gate at the end or something bolted on afterwards, you embed security considerations, practices, and tools right from the initial design phase through development, testing, and into deployment and operations. Finding vulnerabilities early is exponentially cheaper and faster to fix. It breaks down the traditional silos between development, security, and operations teams, making security a shared responsibility.
So security becomes part of everyone's workflow, not an afterthought.
Exactly. A key practice here is threat modeling. This is a structured way to think like an attacker. Early in the design phase, you analyze your proposed system, identify potential threats using methodologies like STRIDE, assess risks, and plan mitigations. It forces you to consider security implications proactively. And of course, at the code level itself, secure coding practices are vital. Things like always validating input, encoding output correctly to prevent injection attacks, using secure libraries and keeping them updated, handling errors gracefully without revealing sensitive information, and absolutely never hard-coding secrets.
How do we automate checking for these things in our development pipelines?
That's where automated security testing in CI/CD is essential. It's a cornerstone of DevSecOps. You integrate different types of security scanning tools directly into your build and deployment pipelines. SAST, static application security testing, tools like SonarCube or checkmarks scan your source code without running it, looking for insecure coding patterns, potential bugs, hard-coded secrets. Great for early feedback to developers. DAST, dynamic application security testing, tools like OWASP Zap or Burp Suite test the running application, actively probing it for vulnerabilities like injection flaws or authentication bypasses, often focusing on APIs. And SCA, software composition analysis, tools like SNAC or OWASP dependency check scan all your third-party libraries and dependencies for known vulnerabilities, CVEs, and sometimes license compliance issues. This is critical for supply chain security.
So SAST, DAST, SEA automated checks running constantly.
Right. The goal is continuous feedback, catching issues automatically and early. DevSecOps isn't just about tools, though. It's that profound cultural shift towards shared responsibility and integrating security seamlessly into the fast-paced development cycles typical of microservices.
Okay, makes sense. Finally, let's talk about keeping an eye on things once they're running. Monitoring, logging, and incident response. How do you get visibility into this complex, distributed system?
Visibility is everything. Centralized monitoring and logging is the foundation. You have to aggregate logs from all your microservices, your infrastructure, your Kubernetes cluster, everything into one central place. Tools like the ELK stack, Elasticsearch, Logstash, Kibana, or Splunk, or cloud provider services are used for this log aggregation. Some key logging best practices. Use a correlation ID, a unique identifier that follows a single request as it jumps between services. This is essential for tracing issues. Use structured logging like JSON instead of plain text lines, makes logs much easier to parse and query. And be careful not to log sensitive data directly, mask, or obfuscate it.
So centralize logs, use correlation IDs, structure them. What about beyond logs?
You also need metrics collection. Tracking key performance indicators, things like request latency, traffic volume, error rates, resource saturation, the golden signals. Tools like Prometheus paired with Grafana for visualization are very popular here. Then there's distributed tracing. This specifically tracks that end-to-end flow of a single request across multiple services, visualizing the call graph and timings. Tools like Jaeger or OpenTelemetry help implement this, and they are invaluable for pinpointing bottlenecks or the source of errors in a complex interaction. And audit logging recording significant security-relevant events and user actions.
Okay, logs, metrics, traces. How do we make sense of all this data and know when something's actually wrong?
That's where alerting systems come in. You configure alerts based on your metrics or log patterns to notify administrators when anomalies occur. The key is setting smart alerts. Alert on symptoms that actually affect users or indicate real problems, not just noisy intermediate metrics. Avoid alert fatigue, where people start ignoring alerts because there are too many false positives.
And if an alert does signal a real incident?
Then you need a well-defined incident response plan. This is absolutely critical in microservices where problems can spread fast. The plan should outline procedures for identifying the scope of an incident, isolating compromised services, performing root cause analysis, patching vulnerabilities, restoring service safely, and communicating effectively. Teams need to be familiar with this plan, practice it, and keep it updated. Runbooks are essential. SIEM tools, security information, and event management play a role here too, correlating security events from various sources, providing dashboards, and aiding investigation.
There's a lot of talk about observability now, which sounds like more than just monitoring. How does that fit in, especially with security?
That's a great point. Observability for security kind of builds on monitoring. It's about being able to understand the internal state of your system just by observing its external outputs, logs, metrics, traces, even for conditions you didn't explicitly anticipate. It helps you ask questions about unknown unknowns, not just track known knowns. For security, this means better anomaly detection, faster investigation of novel threats, and a deeper understanding of system behavior under attack. It really represents that shift from being purely reactive, monitoring for known failures, to being more proactive and investigative. And increasingly, automation and AML are being applied to observability data to spot subtle patterns and potential threats in the sheer volume of data that humans might miss.
Wow. What an incredibly comprehensive deep dive. We've really covered a huge amount of ground, from those foundational principles like zero trust and defense in depth, all the way through securing every layer. network segmentation, IAM, API security, containers, Kubernetes, secrets management, folding security into DevSecOps, and finally, robust observability and incident response.
We certainly have. It's clear, isn't it, that securing microservices isn't just a one-time setup. It's a continuous evolving process. If I had to pick one core takeaway from all this, it really circles back to what we kept mentioning: automation. In these dynamic, complex microservice environments, automation isn't just a nice-to-have for efficiency. It's a fundamental requirement for achieving security that's robust, consistent, and actually sustainable over time. Manual approaches just can't keep up. And of course, that cultural shift we talked about, security becoming everyone's responsibility, that's just as vital as any specific tool or policy.
Absolutely. Automation as a necessity, not a luxury, and security as a team sport.
Yeah.
That really resonates. This raises an important question for the future, doesn't it? If automation is already so critical, how might AI specifically start to transform our approach even further? Maybe moving beyond just automating known tasks to actually predicting and mitigating security risks in real time, maybe even before they fully materialize.
That's definitely the direction things are heading. Using AI to analyze patterns, detect subtle anomalies, maybe even automate responses, it's a fascinating space to watch.
Something for us all to mull over until next time. We really aim to give you a definitive, practical resource today, trying to cut through the noise and get to the most important nuggets of knowledge on securing microservices. If you found this deep dive valuable, please be sure to subscribe to Joy of Architecture wherever you get your podcasts, or your deep dives. We'll be back soon with more fascinating insights to help you stay well informed.